Hello everyone, today we're going to be talking about Physics 252 Week 2 Video Explainer problem number 4. In this problem, we are asked to find the tension in string A in this given system. So this picture right here was given to us in the problem, and it defines what we'll be working with. So as you can see in our problem, I've underlined some of the givens that we need to pay attention to. So the first of which is our horizontal bar of mass m1 and length L. As you can see right here in the problem, we also have a block 2, or block of mass m2, and it is at distance x away right here. So we also have our string A right here, which is distance d away, which is less than half of L right here, distance L. So we're asked to find the tension in the string. And what we can do is we can think of this problem as a torque problem. So for example, let's say that this system was not in equilibrium and it was moving. We could imagine, due to this mass here and the mass of the bar, we can kind of imagine that this bar would swing out this way, and it would be weighted over on this side of the bar, therefore causing it to kind of torque downwards like this. So obviously this isn't happening in the problem, but we can kind of define our system as having a net torque of 0 because it is at equilibrium. So because of this, I've gone ahead and outlined some of the forces in this diagram, because if you remember, our equation for torque here is the radius times force times the sine of theta. And in our equation, or in our problem, we're working with a bunch of nice right angles right here. As you can see, there's just a lot of right angles. So the sine of 90 in our case is 1, so I've omitted this from all of our torque definitions, but you can kind of think of that as being there in this problem. So as I was saying, I've kind of outlined some of the forces that we're working with, the first of which is the force due to gravity on our mass 1. And this is going to occur at the center of the mass because there's nothing weighting this mass unequally, and we have all reason to believe that the center of this mass is at L divided by 2, which would be the middle. So from here, we also have our force due to gravity of mass 2. We also have our tension in string A and our tension in string B. And so using these forces, we can kind of identify all of the sum of the tension of the torques and set that equal to 0. So that's kind of going to be our game plan going forward. So what I've done is I've defined our torques here, and I've kind of written them out. So I think it's kind of important to know, as I was saying, since the center of this mass is at L divided by 2, this is going to be our radius for this torque. And we're going to be using radius x for this torque because it's x distance away, and we also have our distance d here from our problem. So using these torques, we can find the sum of them, and we can set that equal to 0. So since we're using the force of tension from string A in our torque, we can use that to solve for that tension. So as you can see, I've gone ahead and set up this equation here, which we'll be solving algebraically. What I've done is I've pulled out 1/2 to start with. So you can see that came from right here, and which makes us need to multiply these by 2. Then we multiply everything by 2, and we get this right here. We can kind of move this torque 3 in front here, and then we can just kind of solve for the tensile force of string A. So as you can see, I've kind of moved this around, and I've simplified it algebraically here, moving this G out in front and dividing it by 2D. So this would be our equation for the tension in string A. And again, the reason this works is because the system is at equilibrium, and we can define the torques for all of these elements here. So I hope you guys found this video helpful, and thank you very much for watching.